Hi, we're a group of students from the University of Cincinnati, and our hackathon project was on identifying the spatial domains of samarium-doped bismuth ferrite using machine learning. We started out with scanning transmission electron microscopy images from Nelson et al. Then we normalized them and broke them into smaller sub-images or unit cells using a window sliding technique. We had images for samarium doping percents of 0 to 20, and we chose window sizes of 5, 10, 20, 40, or 80 pixels long. We also computed the average ferroelectric polarization vector for each unit cell. Our goal for this project is to create a more efficient and automated process to identify the spatial domains using both unsupervised and supervised machine learning techniques. The first thing we did was compute principal components of our data. What we found is that with increasing window size, the data becomes more ordered, and we also see that most of the variance spreads out across all the PCs. Here's an example of the PCs for the window size of 5 for samarium concentrations of 0 or 7. You can see that most of the variance is in PC1 and that there's very little internal structure to this data. We also computed polarization vector distributions for every window size, and we find that for window sizes of 40 or above, that the polarization vector peaks match the number of domains in the images. We also performed clustering on the data. We used k-means, and we independently selected values of k, or number of clusters, using the Davies-Bouldin and Klinsky-Haribas scores. What we found is that k-means shows the best success with 0% samarium doping and window size of 40. Here are those plots. You can see in the two Davies-Bouldin and Klinsky-Haribas index plots that the optimal number of clusters is 4. Which is an independent verification of our number of predicted domains based on visual analysis of the images and our polarization vector plots. You can also see below the original quiver plot and the plot with our assigned clusters overlaid. We observe that with increased samarium doping, the domains become less well defined, as shown in the superpixel segmentation or k-means cluster assignment plot. And finally, once we get to 20% samarium, the indexes no longer tell us a good number of clusters. We also see that there is very little distinguishable domains in the superpixel segmentation plot. The clustering indices reflect this. We also did machine learning with random forest on all window sizes, and we found that it was capable of classifying the STEM data regardless of the window size. Our conclusions are that tree-based methods are surprisingly good at this problem. Window sizes of 40 or above are suitable for the substrate, and we would finally like to use SHAP analysis on our tree-based model. Some of our drawbacks include how we assigned our cluster labels and the fact that we only have 5 test images, so overfitting is always a problem.